Yeah, so I'm going to talk about how we search for heavy neutrinos using light. But first, a brief introduction. I studied physics in Madrid a long time ago now. And then I did a PhD in experimental particle physics at CIEMAT, which is, as you said, a national laboratory in Spain. I moved to New York to work as a postdoc for a few years, and then I came back to Europe using the Marie Curie Fellowship. And I'm showing here also some places I've been to during my career. So just to give you an idea how international science is. So now let's talk about elementary particles. This is also something very related to the Mediterranean, because since ancient Greece, we have been wondering what are the building blocks of nature, like the Lego pieces that make up nature. And you can see here on this graph, like how this knowledge has evolved during the years. We started with the 4 basic elements: earth, air, fire, and water, back in ancient Greece, and then we started discovering elements until we found all the chemical elements that make up the periodic table. And then we simplified the picture by finding the electron and the proton, but then we started finding more and more subatomic particles, and now we have a lot of them. So now the actual periodic table that we have nowadays is this one. This is what we call the standard model, and we have matter, which is composed of quarks and leptons. And quarks are weird particles because they have fractional electric charges. They have either 2/3 or -1/3 of the charge of the proton. And then we also have the leptons. For example, you probably know the electron, which has a charge of -1 in units of the electron charge. But we also have neutrinos, which is the particles that I'm studying. And in addition to those quarks and leptons, we also have antiquarks and antileptons. Those are antimatter particles that have the same properties as the other particles, but with the opposite charge. We also have bosons that you can see here in red, which are particles that mediate the forces. For example, the gluon is the mediator of the strong nuclear force. We have also the photon, which is very famous, which is the mediator of the electromagnetic force. And we also have the W and Z bosons, which are the mediators of a force that we call weak nuclear. And you may have heard about the Higgs boson, which is related to how those particles get their masses. So just giving you a brief crash course on particle physics, those quarks can form molecules. For example, a proton, the famous proton, is just 2 up quarks and 1 down quark. And if you sum the electric charges, +2/3 +2/3 -1/3 gives you the +1 of the proton. And in the same way, a neutron is 1 up quark and 2 down quarks. So +2/3 -1/3 -1/3 is neutral, like the neutron is. Particles can also experience similar things to chemical reactions in which particles can become new particles. For example, neutrons are unstable and they decay into a proton. This is, you can see here in this diagram, in which one of the quarks of the neutron will emit a W boson and decay into a proton, and this W boson itself decays into an electron and electron antineutrino. So those are like the chemical reactions of the elementary particles. So what I'm looking for? I'm looking for heavy neutrinos. But first, let's talk about the regular neutrinos. The neutrinos are mysterious particles. We don't know how heavy they are, but we know that they are at least 1 million times lighter than the electron. They also have an interesting property, and is that all the particles in the standard model, they either spin to the right or to the left as they travel. They can do any of those two. But neutrinos only spin to the left. And this made physicists to propose a new idea, which is maybe there is a new particle which has not been observed yet, and this is a right spinning heavy neutrino. And this is a way of explaining the neutrino masses, saying they are not really super light. It's simply that they are connected through this seesaw. Mathematically, of course, it's not an actual seesaw, but it's a property of the theory that basically makes that if there is a heavy neutrino which is pushing down the seesaw, then the other neutrinos will appear in our world as very light particles. So I'm trying to search for this heavy neutrino. And how we do that? We use accelerators, which are particle factories. we use those accelerators, which are machines using electric fields and magnetic fields to accelerate and collide particles against a target. And then we use all that energy that is produced in the collision to produce new particles. And how we can do that? Because we have this famous equation, the Einstein equation, energy equal mass times the speed of light squared. So how we make those neutrinos? Basically, we collide those protons against a light target, for example, beryllium or carbon, and then from there we get those quark molecules I was talking to you about before. And those molecules are actually unstable and they decay into things, for example, neutrinos. The point here is that if the heavy neutrinos, they do exist, those quark molecules should also decay into the heavy neutrinos. And you can see here, basically an animation of how the accelerator chain is working, in which the protons are fired and then accelerated in a circular accelerator and then oriented towards the target where they collide and produce the neutrinos. So how do we see the neutrinos? Using detectors, which are devices to study the particle interactions. For neutrinos, because they are neutral, we do not see the incoming neutrino, or in this case, for example, an incoming heavy neutrino, but we see the products of the interaction. So for example, here you can see how an incoming heavy neutrino would be approaching our detector and then decay, produce an electron, which appears like a shower in our detector, an anti-electron, which is this branch here, and then there is an escaping neutrino that you cannot see either because, again, it's neutral. This kind of picture is taken by a detector which is called liquid argon time projection chamber, which basically works like a digital camera. And now we have another property of detectors, and is that, for example, argon emits a flash of light when particles excited. You can see here an example of how a scintillator, this is called a scintillator, is shining light when it's excited. So we can use that light to tell when interaction happened in our detector. And thing here, what we want to exploit is that heavy neutrinos, because they are massive, they will travel slower than the regular neutrinos. So the light from their interactions in the detector will appear in our camera after the light from the neutrinos. So for example, here you can see this is an actual simulation, and this green bunch here is the regular neutrinos, which are very fast. And then this blue bunch here are the heavy neutrinos that you can see they appear later in time, simply because they are massive. So the thing here is, if we can measure very precisely when the lights arrive into our sensors, we can tell the difference between the regular neutrinos and the heavy neutrinos.
2 minutes, José Ignacio.
Yeah, thank you. And here is the actual detector. So you can see here humans for scale. This is the detector being introduced in, this is called a cryostat, which is where the liquid argon is kept in cold. And here is the a picture of the inside of the detector, and all those basically like light bulbs and squares, those are sensors to detect the scintillation light I was talking to you about. So what we have done during the Marie Curie Fellowship, we have used the computer simulations to estimate how many heavy neutrinos we expect in our detector. And basically, this is the result of the study. Here in this axis is the heavy neutrino mass, and here this is basically proportional to how many heavy neutrinos are you producing. And as you can see, SBND, which is the orange line, is the leading experiment in all those masses. So basically, the conclusion is SBND could detect more heavy neutrinos than any other experiment in the mass region that we can explore. And if the heavy neutrinos do exist, we can discover them. So we are going to start taking data in 2024, and we are very excited about it. So just to finalize, just to give you a summary of what I told you, we have matter, which is composed of quarks and leptons. Neutrinos are leptons, neutral leptons. They have no electric charge. Neutrinos may appear to be light, basically because there is a heavy neutrino pushing down a seesaw. We have accelerators we can use to produce these new particles, and we use detectors to see the particles. And this being the detector, that is the one that I'm using, could discover those heavy neutrinos beginning in 2024 when we start taking data. Thank you for your attention.
Thank you very much, José Ignacio. Thank you very much. You are 10 minutes on time. And thank you very much for this quick masterclass of particle physics. And now it's the turn to the students, to the schools to ask some questions. We have 5 minutes, and we have time. So the floor is yours. Schools, Crisa, Vesna, Pilar. Come on.
I hope it was not too difficult.
Now we have Vesna. What's the name of your school, Vesna? Please. So
Oh, okay. I didn't hear.
yes, you have one question.
Yes.
We have a question.
Where are you? Are you in Croatia?
Oh, okay. Yes.
In Croatia, okay.
How does a magnetic field affect a heavy neutrino?
So heavy neutrinos, because they have no electric charge, that means that they will not be affected by either electric or magnetic fields. They just go straight. But for example, here when we are producing the particles, the quark molecules that we use as the first step in the chain to produce the neutrinos, they have charge, and basically we apply magnetic fields to focus them and have like a more intense beam of those particles. So they are what we call collimated, made to be in like a narrow beam, and then we point that to our detector. So basically we get more particles in our detector than if they were flying all around.
Thank you. We have two questions in the chat. We ask these questions, you answer, and we finish, okay? So just these two questions.
Can you read them?
Yes. The first one is, how important is to know some basic things about the specific subject and about science or physical in general? A question from Eva.
I'm not sure. I mean, that's like a very broad question. I mean, basically what we are doing with this is studying like the basic properties of nature. And it's a long way to come here. I mean, you have to study physics, you have to later take a master course and do a PhD. And in the end, what we are using, is basically like a very advanced technology to find like basic properties of nature. And so I would say it's quite important.
Okay. And the question from Samaniego, are you aiming for a Nobel Prize if you find the heavy neutrinos?
To be honest, like nowadays in particle physics, all those things are so big that they are no longer made by just like individuals in the past. Like we are big teams. So no, I'm not aiming for a Nobel Prize, but I hope that me and my team, we're very lucky. We would get to discover something interesting about nature. But yeah, I mean the prize itself is discovering things about nature. The Nobel Prize is not really the target.